So, welcome back, everybody. And now we are honored to have as next speaker, Professor Andreas Wallraff. Since 2012, Andreas Wallraff is full professor for solid-state physics at ETH Zurich, after joining the department in 2006 as assistant professor. Previously, he obtained a PhD degree in physics from the University of Erlangen and worked 4 years as research scientist at Yale University. During his career, he has been awarded with many prizes, to cite some: Nicholas Curti European Science Prize in 2006, a European Research Council in 2009, Max Rösler Prize in 2011, and recently the Helmholtz International Fellow Award 2020. In the lecture today, he will explain how these superconducting qubits, that is, these amazing, I would say, technology work. So, Andreas, thank you very much for joining the conference, and I leave you the stage.
All right, thank you for having me. It's a pleasure to be here and talk at this school. Even though it's not in person, it's still one of the few schools that I lectured in during the Corona time. So it's fun to be back here, and hopefully we'll get a bit of interaction going throughout this lecture. I don't know how you are prepared for taking questions during the lectures as well, or do you?
Yeah, actually, if you want, you can pause at a certain point to answer the question that has been asked, or you can also answer all the question at the end. It's up to you, and we can tell you which are the most interesting or more asked question in case.
All right, good. So I would also plan to do maybe a short break somewhere in the middle of the time that we have, and we can also use that for questions. Also, if you have any urgent questions, just feel free to pose them, I guess, in the chat, and then the organizers can relay those questions to me. Good. So let's see. You still hear me? My computer seems possibly to have an issue. Let's see whether I can. So my slides don't advance now, which is not good. All right, good. So welcome once more to my lecture on superconducting qubits. I should acknowledge at the get-go the contributions of everyone in our lab currently. So I list both the PhD students and postdocs on this title slide, as well as our technical team. And on the title slide, you already see one of our superconducting devices, and it's going to be one of the main actors of this lecture. And on this particular 7-qubit device, we have realized a quantum error detection algorithm based on the surface code. And I'll be aiming at explaining to you everything about superconducting qubits that you need to know, so that you, in the end, you can understand how one would actually operate a quantum error detection algorithm in the surface code on this superconducting device. And beyond the members in our current lab, I should also acknowledge everyone who has contributed to our lab throughout the years. Both students and postdocs who worked with us are listed here, and I also show where they currently are. So I think there's an interesting mix between former lab members who are now faculty at a number of places. There's also quite a few who work for industry that relates to quantum, like, for example, Zurich Instruments, but there's also people working at startups like IQM and Alice and Bob. And I also acknowledge our collaborators both at ETH and elsewhere. So maybe as a good starting point for this lecture, we can take another look at this device, which I showed to you already on my title slide a little bit. So let me walk you a little bit through what you see here on this screen. So the yellow objects are superconducting Transmon style qubit. There's 7 of them. They sit in this double diamond-like structure. Each one of the yellow qubits you can control with 2 control lines. So the pink control lines here are used to apply short, say 10 nanosecond long microwave frequency pulses to the superconducting qubit to control its quantum state. The green lines are used to apply short current pulses to the superconducting qubits. And at the end of this line, the waveguide is shorted. So this current pulse will generate a magnetic field that will induce some flux through the loop, through the squid loop of the superconducting qubit. And that allows us to tune its transition frequency over several gigahertz in a few nanoseconds. And this controllability is used to initiate 2 qubit gates in this architecture. The qubits are coupled to each other through superconducting resonance structures. So these are these turquoise transmission lines here that run from one qubit to the other in this double diamond structure. And through those waveguides, a capacitive coupling between the qubits is mediated to initiate 2 qubit gates. And then in addition, maybe one of the special features of this chip, which actually has enabled quite a few of the experiments that we've done on it, in particular the quantum error detection experiments, are these red and blue elements here, which are lambda quarter coplanar waveguide resonators that are used for reading out the quantum state of the qubit. So the red lambda quarter resonator is the resonator that is directly coupled to the qubit with a large coupling strength and has a strong coupling to the outside world, so a large bandwidth or a large photon decay rate. And this is then coupled to another transmission line that is used for reading out the resonance frequency of this readout resonator through a so-called Purcell filter, which is yet another lambda quarter coplanar waveguide transmission line resonator. And this Purcell filter is needed to actually protect the qubit from spontaneous emission. And one aspect that is also special about this device here is that you see that all these 7 qubits, they have all their individual readout resonators and Purcell filters. And in this device, we can actually read out a group of 4 qubits through the same readout line and a group of 3 qubits through the same readout line. So you see this dark purple waveguide here that couples first to the readout resonator of this qubit here, and then to the readout resonator of the next qubit, and to the readout resonators of this third qubit here. And so essentially these resonators are staggered in frequency so that you can apply a single, say, multicolor microwave pulse to interrogate the microwave frequency resonators coupled to each individual qubit for reading them out essentially simultaneously in a frequency multiplexed fashion. Okay, so now I think I have mentioned all the basic elements on this device here, and we'll look a bit closer at them as we go throughout this presentation. Good, so my lecture is divided in these sections. I'll give you a brief introduction to superconducting qubits and circuit QED. Then I'll move on to talk a bit about single and 2 qubit gates and how they're realized in these superconducting circuits and how we read out our superconducting qubits. And in the final part of this lecture, I'll apply everything we have looked at and learned to discuss this quantum error detection experiment, which is a step towards realizing quantum error correction in superconducting circuits, which is essential for realizing fault-tolerant quantum information processes, which is the target goal in quantum information science and in the realization of quantum computers. Okay, so that's about the schedule that we have ahead of us today, and I plan to have a short break in the middle to take some extra questions and maybe for you to take a little break throughout this lecture. Good, so let's start talking a little bit about superconducting qubits and how they're coupled to microwave frequency oscillators to realize this concept of circuit quantum electrodynamics. So you all know about conventional circuit elements. Electronic circuits are made from capacitors, inductors, possibly resistors, and nonlinear circuit elements such as diodes, which you can then use to form transistors. And these form the basis of all the communication and information processing technology that is based on, say, classical information processing ideas that we make use of every day. And this has seen a long history from the invention of the first nonlinear semiconductor element, the transistor at the Bell Labs, that then got integrated to amazing integration depth with several billion of transistors on these centimeter-sized chips that we use today to process information also in my computer that just had my PowerPoint file crash recently. So when you look at how to describe the physics of these electronic circuits, while the materials properties need some quantum physics to understand them, for example, to understand how isolators and metals and semiconductors can be distinguished from each other, all the information processing on these circuits is based on classical physics phenomena. So quantum mechanics is not involved. The superposition principle is usually not important, and any of the control fields that we use are not quantized. And so maybe the first question that you ask yourself when you think about using superconducting circuits in the context of information science or in the context of doing quantum physics experiments is, how do you need to operate these basic circuit elements to observe their quantum mechanical properties? So and here I have probably an oversimplified example, but I still like it as a starting point. So we are considering these basic elements, capacitors and inductors, for example, and we can see what charges and currents do on these circuit elements. So one very simplified way to look at things is that you can consider such a capacitor here. And if you consider a single electron, we know that charge is quantized in form of electrons. We could have the choice of putting that single electron on either one of these two capacitor plates. And classically, you have these two choices, but quantum mechanically, that single electron could be in a superposition of being on either one of the two capacitor plates. And if one wanted to, one could write this as this little pictorial wave function. So that's in principle, according to the microscopic quantum physics of particles like electrons, this is an allowed quantum mechanical state of an electronic circuit. Even though that under usual circumstances, we rarely observe that, in particular not under room temperature conditions. So then you could also consider taking an inductor and enclosing this inductor in a loop, and you could consider a current flowing, say, clockwise through this loop here. And classically, you would imagine that that macroscopic current that is now made up of many millions of electrons would either flow clockwise in this loop or counterclockwise in this loop. But quantum mechanically, this current could be in a superposition of flowing clockwise and counterclockwise. And in a pictorial wave function depiction, you would maybe show this situation like that. And that's already maybe a little less obvious that that could happen, because now you're not talking about the quantum physics of an individual microscopic particle like the electron on the capacitor, but you rather consider the quantum physics of a collection of electrons that behave coherently to form this superposition state of currents flowing clockwise and counterclockwise. So maybe one of the most basic approaches to understand the quantum physics of these electronic circuits, I think, is to realize that charge and flux are special variables to describe the physics of these systems. So the charge, like the charge Q that describes the charge on this capacitor, or the magnetic flux phi that is generated by the current that flows through such a loop, that current creates a magnetic field, and that magnetic field creates a magnetic flux through the area of the loop. And so charge and flux in electronic circuits have a special role. They're conjugate variables, like the position and the momentum are the two conjugate variables for a particle moving in free space. And when you first learn about quantum physics, you learn about the quantum physics of this free particles and how they interact with potentials. And to go from sort of a classical description of the motion of a free particle to a quantum description, you promote these conjugate variables to quantum operators, and you then have promote your Hamiltonian function to a Hamiltonian operator. And then if you have that Hamiltonian operator, you can start solving Schrödinger's equation with it and make a quantum mechanical analysis of the problem that you're looking at. And so essentially you can do the same thing that you've learned in your first quantum mechanics class for electronic circuits by making this realization that charge Q and flux phi are the conjugate variables that describe the dynamic properties of the system. So, and because these are conjugate variables, there is an uncertainty relation that holds between them, similar as the uncertainty relation that you know for position and momentum of a particle. And And there's also a commutation relation between the operators that correspond to charge and flux. So for example, maybe I spent a moment to now look at the next more complicated example, which is combining inductors and capacitors in this oscillator circuit. So here you see a combination of a linear inductor and a linear capacitor. And when you create these circuits, say in an integrated superconducting device, you can choose capacitance and inductance values that make you end up with oscillators that have a frequency of several gigahertz or so, say 5 gigahertz in this case. And on the side of this picture here, I list a few typical circuit parameters for that. So an inductor, like if you have a straight piece of wire, it has an inductance of about 1 nanohenry per millimeter. So if you coil up a millimeter of wire on the circuit, you get a nanohenry of inductance. And if you make a capacitor of about 1 picofarad, the combination of that inductance and capacitance gives you roughly a resonant circuit with a 5 gigahertz resonance frequency. And so how do you think about the quantum physics of this circuit? Is you first start out with writing down the total energy for it. And that's a combination of the magnetic energy stored in the inductor by currents flowing through this inductor and the electric energy stored on the capacitor. So that's the flux squared divided by twice the capacitance, is the magnetic twice the inductance, is the magnetic energy, and the charge squared divided by twice the capacitance is the electric energy. And now knowing that there is a commutation relation between flux and charge, you can write down the operators for flux and charge and then replace these conjugate variables with the corresponding operators and then find this Hamiltonian here, which is quadratic in the 2 conjugate variables, flux and charge, which is characteristic for these harmonic oscillators. Yeah, and then you've solved harmonic oscillators many times in your quantum physics classes, and you know that in second quantization, its Hamiltonian can be written with these raising and lowering operators in the following form. And the prefactor of that is Planck's constant times the resonance frequency of the harmonic oscillator. And so this then allows you to see that this electronic circuit here is actually quantum mechanically described by a harmonic oscillator with an infinite number of states that you label from 0 to n, where the separation between the states is equidistant and given by Planck's constant times the resonance frequency of the electronic circuit. Yeah? And sort of in this way, you can essentially go ahead and quantize any electronic circuit that you could design or draw or make in your lab. And here you can already, one way how we like to talk about the excitations of these harmonic oscillators at microwave frequencies, we like to think about them as storing microwave frequency photons. All right, so in which ways can you create these harmonic oscillators that I've discussed here? There's actually quite a number of different approaches. You could go ahead and realize this inductor-capacitor combination that I've just shown on the last slide by making a long wire that coils up here and an interdigitated capacitor that you see on the right-hand side here. And this essentially realizes a combination capacitor. You could also make these harmonic oscillators by just drilling a hole or making a cavity in a 3-dimensional block of metal. And this hole in this 3-dimensional block of metal now supports electromagnetic modes. It supports a number of these modes, but around the resonance frequency of each one of these modes, you could describe that mode as a single harmonic oscillator. Or one aspect that you've seen already in my title slide and that we make of use a lot is you can make this coplanar waveguide resonators that actually are made from a superconducting wire that is surrounded by a ground plane that then meanders across a chip between sort of an input coupler and an output coupler. And that is also forming a harmonic oscillator with a number of resonant modes and next to the resonance frequency of each of these resonance modes. This is described by the Hamiltonian that I've shown on the last slide. Or you could also consider, say, weakly anharmonic resonators. If the anharmonicity is weak enough, you could also describe those in good approximation as harmonic oscillators. So one of the aspects that is maybe a bit boring about these harmonic oscillators is that all their resonance frequencies or all their energy level separations are exactly equidistant, and it's hard to address individual transitions between these different excitation levels of harmonic oscillators. And therefore, one would consider making these oscillators anharmonic, so get rid of this linearity in the energy level spectrum. And one of the ways how that's done in superconducting electronic circuits is to replace this linear inductor L here by essentially an ideal nonlinear inductor. And this ideal nonlinear inductor is realized as a so-called Joseon tunnel junction. And in the linear inductor, as we've just learned, the magnetic energy is proportional to the square of the flux that is generated by the current flowing through that inductor. In a Joseon tunnel junction, there is a current flowing through the Joseon tunnel junction, and that the magnetic energy that is created by that current is a cosinusoidal function of the flux that the current generates. So this cosinusoidal dependence on the magnetic flux is distinct from the quadratic dependence on the flux in this linear oscillator, and this cosinusoidal dependence actually makes this oscillator then anharmonic through this nonlinear inductor. And I'll explain in a few in another slide a bit how this nonlinear inductor works. So this cosinusoidal dependence of the magnetic energy on the flux then leads to an energy level spectrum in which the different energy levels are non-equidistantly spaced from each other. In particular, the ground to first excited state transition frequency is larger than the first to second excited state transition frequency, which then again is larger than the second to third excited state transition frequency. And there's one really very simple and intuitive way to see that. So for example, you can think of this harmonic oscillator circuit here as a particle moving in a potential, and flux and charge are conjugate variables. So you can choose a basis, either the flux basis or the charge basis. And if you choose the flux basis, then the potential energy term is quadratic in the flux variable. It's just the magnetic energy. And the particle is then a particle whose mass is determined by the capacitance of this capacitor. And you could think of it as this particle moving in this quadratic potential. And then if you quantize the motion of this virtual particle in this quadratic potential, you find these equidistant energy levels. So if you now replace your inductor by a Joseon tunnel junction, you get this cosinusoidal dependence on the flux variable. And this cosinusoidal potential then opens up to higher energies in comparison to the quadratic potential. And because the potential energy landscape gets wider at higher energies, or so the energy levels actually move closer to each other. And then if you quantize the motion of a particle moving in this cosinusoidal potential, you will find exactly the situation that I've described on the previous slide, that the ground to first excited state transition frequency is a little bit larger than the first to second, and so forth. And towards the top of this potential here, the energy levels get closer and closer to each other. And so this anharmonic superconducting circuit, where the linear inductor is replaced by this Joseon tunnel junction, that then forms this anharmonic energy level spectrum in which we can now address transitions between the different states by irradiating it with microwave frequency radiation that is resonant with a specific transition. So we can now, through that radiation, couple specifically the ground state to the first excited state, for example, by picking the right frequency and not coupling the first excited state to the second excited state simultaneously, which would happen in a linear oscillator. Okay, so since this is a lecture, I think it's maybe good to think briefly about where this cosinusoidal dependence on the magnetic flux in the Joseon tunnel junction comes from. So the Joseon tunnel junction, which is symbolized in an electronic circuit by this box with a cross through it, it's based on the Joseon effect, which Brian Joseon discovered during his PhD work at Cambridge quite some time ago. And so what he found when he analyzed this Joseon tunnel junction, which is a tunnel contact between two superconducting electrodes, he derived a set of equations that describes the currents flowing through that junction and the voltages appearing across it. And actually, it turns out there's two so-called Joseon relations, a DC and an AC Joseon relation that are written down here. So the DC Joseon relation says that the current flowing through the junction is a critical current times the sine of some phase difference delta across the junction. And this phase difference delta that is indicated here. So in the superconductor, the electrons condense into a Bose condensate of electrons in each of the two electrodes. And this Bose condensate is described by a wave function whose prefactor is proportional to the density of the electrons in the electrode, and the wave function has a phase factor that is where the phase factor is exactly given by this phases delta 1 and delta 2. And the phases of the wave functions in the two electrodes can be different from each other. And what the DC Joseon relation says is that the current flowing through the junction is actually given by the sine of the phase difference of these wave functions. Then the AC Joseon relation says that the voltage occurring across such a Joseon tunnel junction is actually proportional to the time derivative of this phase difference delta. And that proportionality is set, or the proportionality constant is set by the so-called flux quantum. So in superconducting circuits, the magnetic flux is quantized, and the quantization constant is phi naught, which relates to Planck's constants and twice the electron charge. And so with these two Joseon equations, you can actually try to learn what the inductance of a Joseon tunnel junction is. And the inductance in any electronic circuit relates the voltage to the time derivative of the current. And if you use these Joseon equations to write down this relation, you actually find that the inductance has this specific form here, namely it's proportional to 1 over the cosine of this phase difference delta. And this prefactor is called this specific Joseon inductance, and it relates to this Joseon flux quantum and the critical current across the junction. And so now you can think of what is the magnetic energy stored in this junction, and this magnetic energy can be found by integrating the product of the voltage and the current across the junction. And there you find that this Joseon energy is proportional to this prefactor, which is the product of the critical current times the flux quantum multiplied by the cosine of this phase difference delta. And that's actually where this cosinusoidal dependence of the magnetic energy in the Joseon tunnel junction comes from. And then you can ask yourself, okay, what is this energy scale, this Joseon energy? And it depends on the critical current of the Joseon tunnel junction, so the maximum current that can flow through it without any dissipation occurring. And say if you would consider 100 nanoampere maximum current, that would give you a Joseon inductance of about 3 nanohenries, and that corresponds then to a Joseon energy of about 50 gigahertz or so. So your cosinusoidal potential is about 50 gigahertz deep. So from the bottom to the top of the cosine is 50 gigahertz, when the critical current of the junction is 100 nanoamperes. And so that's essentially what gives these superconducting electronic circuits their nonlinearity. Good, and the Joseon tunnel junction itself, I mentioned it already, is made from these two superconducting electrodes that are separated from each other by a tunnel barrier. And typical materials that are used are, for example, aluminum for the superconducting electrodes and aluminum oxide, which forms a nice tunnel barrier that separates the two aluminum electrodes from each other. And this typically gets then fabricated using electron beam lithography techniques in a clean room. And here in this picture, you see a horizontal superconducting strip, a vertical superconducting strip. And in this area where the two overlap, they form a Joseon tunnel junction. And the area of that tunnel junction is given geometrically. And the critical current of the junction is essentially set by the density of the electrons in the two electrodes and the tunnel resistance across the junction, which is given by the essentially the thickness of the tunnel barrier between the two electrodes. And so this gets fabricated in a clean room, typically in techniques that are known as shadow evaporation, for example, but there are also some alternatives. Good, and with these elements, with linear inductors, linear capacitors, and these nonlinear Joseon junctions, you can build many flavors of superconducting quantum bits. Here you see a selection of photographs of quantum bits that have been made from superconducting circuit elements. Maybe I'll mention a few more explicitly. So one of the very first ones that were investigated was this Cooper per box qubit. So that was work in a group of Syrah-Saclay that started more than 20 years ago now. The currently probably most successful or most widely used superconducting qubit is the so-called Transmon Qubit. If you're interested in the details of that, you could read this paper by Jens Koch from 2007 that introduced this qubit, and it's really that or versions of it are used in all the quantum computers at IBM, at Google, and in most of the labs that work on superconducting quantum bits. And there's variants of these transmons, like one of the interesting names is that every time you come up, one of the interesting aspects is that every time you come up with a different circuit, you can give it a name. And so you can play chemist from the early days when you identified new elements, you were free to give this new element a name. Now when people actually invent new superconducting circuits, they invent names for those. So one of our graduate students already some time ago made this kind of interesting looking superconducting qubit and named it the Jellymon. And maybe interestingly, at times there's heated discussions about what names are appropriate for these circuits. So there was in the community around superconducting circuits, there were questions about how different a Cooper pair box is from a transmon or an Xmon, which interestingly all have exactly the same Hamiltonian that describes its physics, but the circuit is actually used in slightly different parameter regimes, and then has found these names that now are widely used. Good. So how does one operate these superconducting electronic circuits quantum mechanically? So here's one of these nonlinear oscillators that I mentioned, the parallel combination of a Joseon junction and a capacitor, so that you then need to probe in some form. And one of the ways to probe it is you could take a microwave frequency radiation source connected through a coupling capacitor through this to this superconducting qubit, and do a scattering experiment, maybe similarly as you would take a laser and shine a laser on an atom and look at how the laser light scatters from the atom. And the scattered light in superconducting electronic circuits you collect by coupling another coupling capacitor to your qubit, and maybe trying to guide the scattered microwave radiation towards a microwave frequency amplifier that then amplifies the signal, which you can then digitize and see what you can learn about the circuit from that digitized signal. So what do you need to do to observe the quantum properties of this superconducting qubit? And so here's my little 3-step recipe. So the first one is to avoid dissipation. So using superconductors is good. So because if you use normal metal components, any currents flowing in these normal metal components will dissipate heat through the resistance of these components. And this dissipation would lead to the energy relaxation from higher excited states back to the ground state by just leaving energy behind in these resistive components. So therefore, all the circuit elements need to be as lossless as possible. So the second aspect that is important, if you were to operate such a gigahertz frequency circuit, so where the typical energy level separations are on a scale of a few gigahertz or possibly a few tens of gigahertz, if you would operate that at room temperature is a much, much higher energy scale than 10 gigahertz, say. So a good number to remember is a gigahertz of transition frequency corresponds to 50 millikelvin of thermal energy. So 10 gigahertz transition frequency qubit corresponds to sort of a 500 millikelvin equivalent excitation energy. And so if you take such a circuit and operate it at 300 Kelvin, even if you ignore the fact that it's not superconducting, then it would be in a highly excited thermal state. And therefore, you just take your whole circuit and cool it down to temperatures which are much less than this typical energy scale of the transition frequency. So we cool the circuits to 10 millikelvin roughly. And then the other aspect that is important in circuit design and posed a challenge, at least initially when these circuits were designed, is that you need to isolate the quantum circuit properly from your control and your readout electronics. And so you see that there's this coupling capacitor through which you couple the input radiation to your circuit, and then there's a coupling capacitor through which you couple the detector to the circuit. And yeah, if this coupling is too strong, you could imagine that if you have an excitation in the superconducting electronic circuit, that excitation could actually leak back into the control electronics, which is certainly undesired, and it could leak back into the readout electronics. And maybe the readout electronics leakage is good when you want to actually detect the state of the quantum circuit. But in case you don't want to detect the state of the quantum circuit yet, that leakage of energy through these coupling capacitors is certainly not good. And therefore, you need to control the coupling strength for your control and readout electronics to the quantum part of the circuit well, so that you can preserve the coherence of the quantum circuit. Good. So this is a slide that I wanted to show you later, and that probably got lost in the crash of my PowerPoint. So maybe the next step that is interesting to discuss briefly is the capabilities that arise from combining linear oscillators with nonlinear oscillators in superconducting circuits. And we've just discussed these linear oscillators that can be realized as discrete LC oscillators, as coplanar waveguide transmission lines, or as 3D cavities created by holes in metal blocks, and superconducting qubits that are created by combining these nonlinear inductors with capacitors and possibly also with linear inductors. And so there's an interesting concept that superconducting circuits inherited from atomic physics and from essentially AMO physics, which is known as cavity QED. And in cavity QED, you investigate the interaction of, say, atoms or two-level systems with optical frequency transitions and an electric dipole moment with optical frequency radiation that is contained, say, in a high-quality mirror-based cavity. And if your two-level system has a dipole moment that is of a significant size, and the electric field generated by the photons stored in this cavity, then the two-level system can absorb individual photons from the cavity mode and coherently re-emit them into the cavity mode. And this happens at a coupling rate that is known as G, and this coupling rate G is proportional to the field strength created by individual photons inside the cavity and the dipole moment of the two-level system. And this is a convenient interaction, or also a useful interaction, because it allows one to convert quantum states stored in an atom into photons. And the superconducting electronics version of that is shown here. So there's a kind of this nonlinear atom-like circuit, and there's the linear cavity-like circuit, and the two are coupled to each other through this electric coupling capacitor. And this coupling essentially creates the equivalent of the dipole interaction between the radiation field inside the cavity and the dipole moment of the qubit. And this is some piece of physics that has been investigated a lot in AMO physics, and Serge Haroche got a Nobel Prize for this a few years back. So why is this cavity QED idea so useful in quantum information processing? So first, it can be used to isolate qubits from their electromagnetic environment. So when you take say a superconducting qubit or an atom, it doesn't really matter. And if you detune its transition frequency from the cavity resonance frequency, then you can actually suppress the vacuum fluctuations of the electromagnetic field present in the cavity to levels that are below the vacuum fluctuations of the electromagnetic field in free space. And the strength of this electromagnetic field and its dipole coupling to any two-level system actually sets the lifetime of the two-level system. And so if you suppress the vacuum fluctuations, you will increase the lifetime. So this can be done in cavity QED physics. And actually, the very first cavity QED experiment ever observed that the lifetime of an atom was increased by bringing it in between two mirrors, whose separation was small enough that the wavelength of the photon that the atom is trying to emit was longer than the separation between the two mirrors. Okay, so this allows you, bringing a detuned two-level system into a cavity allows you to enhance its lifetime. And it allows you to do so while maintaining addressability of the qubits. So you could still change the qubit state by injecting radiation into the cavity at the appropriate detuned frequency. So one aspect about this combination of two-level system and harmonic oscillator, which is very useful, is that it can be used to read out the state of the qubit. And so I'll discuss that later in this lecture. So when the qubit is detuned from the resonator, actually the resonator inherits a frequency shift from the qubit that depends on the quantum mechanical state of the qubit. So the resonator will have a frequency that is different depending on whether the qubit is in the ground or in the first excited state. And that's something that is virtually used in all of the experiments on quantum physics with superconducting circuits. Then instead of coupling a single qubit to a harmonic oscillator, you could decide to couple multiple qubits to the same oscillator. And in this way, different qubits could couple to each other by exchanging photons through this oscillator, either virtually or exchanging real photons through the oscillator. And then there's also this aspect that I've mentioned before. You can use this coupling between the two-level system and the cavity to convert the state stored in a stationary qubit into a photon. And then you could emit the photon into a fiber and, for example, send that photon to another experimental setup. And this also works for superconducting circuits. If you couple a transmission line to this cavity mode, you can actually launch a photon into that transmission line and send the photon elsewhere, say to a different cryostat, for example. All right, maybe a few more words on cavity QED. So I've mentioned this basic aspect already. So we consider this atom inside the cavity and the interaction with the radiation field at this interaction rate G. And there is a very simple Hamiltonian that describes the physics of this system. And this Hamiltonian has just this harmonic oscillator part. It has a two-level part. And then it has this interaction part where A dagger and A are the creation and annihilation operators of the radiation field inside the cavity. And sigma minus and sigma plus are the operators that swap the qubit from the ground to its excited state and back. And so this basic Hamiltonian describes the physics of cavity QED. And what one looks for essentially is the situation where this coupling strength G in this Hamiltonian is much larger than any of the rates at which decoherence occurs. Yeah, for example, the rate at which you lose the photon from the cavity, or the rate that your two-level system might decay into a mode not captured by the cavity. So if you look at this Hamiltonian, there's one way how to easily interpret the physics of it is to draw a so-called dress states energy level diagram that is shown here. And on the right-hand side, a specific situation is considered, namely the situation where the resonance frequency of the cavity, omega r, is chosen identical to the transition frequency of the two-level system. And so if that is the case, a state where the cavity has one photon and the two-level system is in the ground state, or where the cavity has no photon and the two-level system is in the excited state, are at the same energy. And if that's the case, and the two are coupled by this dipole coupling strength, this dipole coupling will hybridize these two states and lead to a splitting, so that you essentially form a molecule between the photon in the cavity and the excitation in the qubit. And this is known as the vacuum-Rabi mode splitting, and the size of this splitting allows you to directly measure this dipole coupling strength between the two elements. And this dipole coupling strength, for example, limits how quickly you can exchange the excitations between the cavity field and the qubit. And the holy grail of cavity QED is to reach this limit where this dipole interaction strength is larger than any of these dissipative rates. And this was something that was an experiment that we did for the first time with superconducting circuits in 2006 when I was at Yale working with Rob Shirkoff and Steve Gervin and Alexandre Blais on the theory side. And this coupling you can observe either spectroscopically by measuring this energy splitting, or you can also measure it in a time-resolved measurement by measuring these so-called vacuum-Rabi oscillations. And another important aspect that relates to this capability to read out superconducting qubits actually considers this Jaynes-Cummings Hamiltonian that I've mentioned in a situation where the qubit transition frequency is detuned from the cavity frequency, such that the difference between the two frequencies is much larger than the coupling strength. And then an interesting piece of physics happens that you can analyze when you look at this Hamiltonian here. So this is a Hamiltonian which has been appropriately transformed to diagonalize it when the two systems are detuned from each other. And what you see now is the term that has the A dagger A, which essentially counts the photon in the resonator, has a resonance frequency where the cavity resonance frequency is now qubit state dependent. So it's changed by the amount coupling strength squared divided by detuning times sigma z, which is then the expectation value of the qubit state operator. So if the qubit is in the ground state, sigma z is +1. If it's in the excited state, it's -1. And so therefore the resonance frequency of the cavity is shifted by either g squared over delta downwards or g squared over delta upwards, dependent on the qubit state. And this can be used to read out the qubit state experimentally. And actually, it also performs a quantum non-demolition measurement of the qubit state, because this Hamiltonian commutes with the qubit state operator. And so a pictorial way to look at that, so you have the bare cavity at some resonance frequency. If the qubit sits in the cavity in its ground state, the resonance frequency will shift downwards. If it sits there in its excited state, the resonance frequency will shift upwards. And now you can simply look at the transmission amplitude and decide by that transmission amplitude measurement whether the qubit is in the ground state or in the excited state. Good. Maybe let me skip this slide and maybe finish this first part here with a few more general comments. So there's research on these superconducting circuits gets done in quite a number of academic labs. I think by now there must be more than 100 that master the capability of making these superconducting quantum electronic circuits and observe their quantum mechanical features. What is maybe also interesting is that there is now lots of industry that is interested in using this technology to build quantum computers, and not only large established industry like IBM and Google, but also startups like Rigetti or IQM, for example, that invest into this technology to master it for building quantum computers. So these devices that you've seen on this last slide here are devices that are made at these different companies and startups. And maybe to give you an impression what things look like in our own lab. So this here is a picture of a superconducting circuit that has 17 qubits mounted on it and sits in the sample holder here with 48 microwave frequency ports through which you can apply all the signals to this qubit that you need for changing its state, for tuning its transition frequency, for reading out the qubit states, for example. This sample mount then, or the sample then goes into a sample mount where it's protected from environmental radiation and shielded from magnetic fields. So you see, for example, here's this aluminum cap, which is good for magnetic field screening. The whole assembly is in a radiation-tight copper box, and there's 48 connectors leading to microwave cables that lead to room temperature. Then shielding these superconducting circuits from external magnetic fields is important. So here you see mu metal magnetic shields and an assembly of different parts that we use to mount the sample holder that you saw, or the sample puck that you saw on the previous slide, into a dilution refrigerator. And here you see sort of the assembly that includes this 48-port sample mount with several layers of magnetic shielding, and then all the wiring that is needed to address all the qubits in such a setup. And this whole thing then sits in a commercial dilution refrigerator. So this one here has been set up by the people you see here. Johannes Heinzo is now working for IQM in Finland, and most everyone else is still in our lab at this stage. And then once you've, okay, so on this picture here, you see the sample mount sit at the bottom, and then there's wires that go up through the different temperature stages to room temperature. And there at room temperature, you connect your wires to microwave frequency control electronics. And together with this ETH startup, we're actually doing quite a bit of electronics development to have everything available that we need to run quantum experiments with several tens of qubits. So then if you have 17 qubits in your device or so, your electronics starts to get a bit more involved. And so this is kind of a scan across our current electronics setup. And you see there start to be quite a few cables that you need to handle in controlling your superconducting circuits. Good. So I think this would conclude the first part of my presentation. And I think now would maybe a good time to possibly take a few questions and maybe take a break. Also, maybe depending a bit on how much of the time we have to make up towards the lunch break. So maybe that's I would maybe take first a few questions and then maybe with Uwe or Francesco, we can discuss how we do the timing for the rest of this lecture.
So yeah, we have a question actually. And the question is, what is your approach to deal with the increasing complexity of the system with increasing number of qubits? Concrete, how do you plan to reduce the number of inputs and outputs?
Yeah, that's an excellent question. So one of the measures that we have taken is we, for example, on the readout side, we're now multiplexing the readout. So previously in many experiments and also in quite a few of the experiments at IBM, for example, the qubits are read out individually. So here we are now capable of reading out many qubits simultaneously through a single wire or through a pair of wires indeed. And multiplexing will be essential. So at the moment, we only multiplex on the qubit readout side. But I think it would be interesting to think about how to multiplex on the qubit control side as well to reduce the wire count. And this will certainly be an important question to address while scaling up system size.
Okay, we have another question actually. Do you plan to embed the superconducting circuit, the whole circuit, or even each one of the qubits into something like phonon band materials that could improve the coherence times?
Okay, so there's a question like how large is the interaction between the superconducting qubits and maybe phononic degrees of freedom on these devices. And one needs to investigate the coupling mechanism there. And so the superconducting qubits store their quantum state in an electrical degree of freedom. And this electrical degree of freedom creates electric and magnetic fields near the device. And if it's mounted on a substrate that couples to these electric and magnetic fields, for example, because it's piezoelectric, it would launch, say, surface acoustic waves or bulk acoustic waves. And Uwe can probably tell you a lot about that. And in our devices, we actually try to avoid that by using materials that at least genuinely have weak coupling to electromagnetic fields. But certainly if in the case that phonons start to play a role in these devices, and nominally they should be cooled down to very low temperatures because they sit in the same dilution refrigerator. If those start to be a problem, indeed doing phononic bandgap materials could be a relevant approach. Yeah, that's a good suggestion.
Okay, thanks. So there is a third interesting question. So can you tell about any efforts in the direction of coupling these superconducting qubits with hyperfine qubits in ions or atoms?
Yes. Indeed, a long time ago, we were working or thinking about doing something like that with Hartmut Heffner, for example, on the ion side. There's always been activities where one looks at hyperfine transitions, which are also in the microwave frequency domain, which could couple to these waveguides. And there's a number of groups that work on that. And we also do a few hybrid experiments ourselves. And these hybrid experiments are all very, very challenging, essentially because you add another technology that you need to master as well. And probably practically what has happened is that the progress on superconducting circuits was so fast that the hybrid technologies really have a hard time sort of to hold pace. So I think while what you suggest is really technically feasible, it's a big effort, and one needs to make sure that the hybrid system actually has improved properties relative to, say, the clean, simple system on which is based just on one technology. I think it's certainly something to consider when it's needed, but one needs to also make this hybrid technology have properties that are at least as good as, say, the best property in your of the devices that you work with otherwise.
Okay, thanks. So I will say last question, and then we can take a 5 minutes break so that everybody can rest a bit. So what would be the limitation in manufacturing qubits using high temperature superconductors?
Okay, so that's also an interesting question. So what role does temperature really play in these experiments? And these cryogenic systems are commercial. They're really a solid technology that now exists since many tens of years. And moving to higher temperatures is really not that advantageous at this stage, because cooling them down is not as difficult as one might think. So going to higher temperatures then would also require to keep the thermal excitation in these circuit elements low. That would then mean, so higher temperatures, you could actually use high temperature superconductors so that the materials themselves stay superconducting, but you still need to avoid thermal excitation. So the transition frequency in the qubits would also need to be high, in which case you then need control electronics that, rather than working, say, in the range of 5 to 20 gigahertz or so, you would need control electronics that works in frequency ranges of several hundreds of gigahertz. And that is actually pretty impractical and expensive, and there's less good technology available there. So that I think the gain from working at higher temperatures is not high enough currently to justify considering that.
Okay, so thank you, and thanks everybody for the interesting question. We can rest for 5 minutes, and we meet again at 11:10.
Good, and maybe I would have still for you a question. So what ending time do we target now?
Now we can also end at 12:45. I think it would be good enough. What do you think, Uwe?
Wasn't that on the schedule? It said 12:45 anyhow.
Sorry.
Yeah, but we had some delay in the beginning, right? So maybe if we overshoot by 10 minutes or something, that's
okay. So shortly before 1 would be okay, you're saying?
Yeah,
so.
yeah.
Mm-hmm. Good. So that, I think that should be fine. I'll aim for that.
Cool.
Good. Or a student is very good.
Andreas, I noticed you have a lot of really nice figures and pictures.
Yeah.
Is there someone in your group who's just really good at Photoshop, or do you use this ETH service?
No, this is all. I think we all did ourselves more or less. I think so. I worked like between high school and university. I worked in graphics. A bit, so I did computer animations and things like that while at the end of my high school, essentially, and I did some technical documentation for a company for some while, and and then I kind of published a newspaper for hospital for a year or so, and so
So you know a bit what to look for.
I kind of, yeah, I have some experience with these things, and
that's an interesting thing we'll mention next time in your CV introduction.
Yeah, definitely. I do like this. This was at the time, so it's like a long time ago now when desktop publishing and things like that were starting to be a thing. Yeah? So before many of the things were done kind of manually. Yeah. And then people started to do animations, computer-based, and also all this publishing business all turned digital and sort of graphics-based. And I spent some time there, and even I think at the time I also thought that one could have founded a company and that would have probably made some money initially, like in the early days of that.
Probably if it's like really growing field. And...
Yeah, I think it was clear I had good experience with that and was growing. And I think there's certainly a niche until all the big publishers and the advertisement houses and so on learn the technology. There's certainly a gap where you can kind of position yourself well, I think. And so I think that's where my my interest comes from in having nice graphics. And then there's certainly people others in our lab who have an interest on that. So I think this one here is from, I think Yves Salate put that together. It's on the title of his PhD thesis. He's now at Zurich Instruments.
Okay, Francesco.
Yeah, I would say we can start again. Actually, there is another question. I don't know if you want to answer it before.
Sure.
Okay, so the question is, why don't we use signals phase while performing the dispersive measurement? Generally, first measurement give more accurate result than intensity measurement. This is the question.
Yeah, so I'll in one of the coming slides, I'll say a few words about readout, and maybe I can come back to that then.
Okay.
Good. So then let's restart. So in the first part, I've told you about superconducting qubits and this concept of circuit QED and how it's useful for quantum information processing. And now in the remaining part of this lecture, I'll tell you a little bit about single and 2 qubit gates and also Qubit Readout, and then deploy that essentially to tell you a bit about quantum error detection in superconducting electronic circuits, which is an experiment that we did about a year and a half ago or so. Okay, so here is my one slide description on how to control single qubits. I think this should all be quite familiar to you because it essentially works the same way as it works in any quantum mechanical 2-level system. So you identify the energy level spectrum of the system by doing some spectroscopy initially, and then you can pick the transition frequency. And then instead of switching on your microwave source continuously, as in spectroscopy, you apply a short microwave frequency pulse. And then the combination of the pulse amplitude and the pulse length will actually lead to a certain rotation angle of your qubit state and its qubit state space. And here you see this block sphere representation of a single qubit state space. And on the right-hand side, you see the real and imaginary part of the density matrix and the expectation values of the X, Y, and Z Pauli operators. And what you see on this slide is all measured data. So these density matrices and the expectation values of the Pauli operators are all measured. And what is done in this experiment here is one applies a pulse with a certain phase and varies the amplitude or length to make this qubit state vector rotate around this Bloch sphere about 2 different axes, namely about the x-axis and the y-axis. And the qubit state is then identified by performing a measurement, and how this measurement works, I will say a bit more on later. So here, for example, if you choose a certain pulse length, you will do a quarter rotation around this the qubit Bloch sphere, in this case about the x-axis. And then if you just double the length of the pulse or double the amplitude of the pulse, you will rotate it by exactly twice the angle, and that qubit state vector will then go towards the south pole. So now it's an equal superposition state on the equator. And essentially what sets the axis about which one rotates this qubit state vector is the phase of the microwave frequency pulse that is applied to the qubit. So here we chose one phase, and then if you change the microwave phase by 90 degrees, you will actually rotate about the y-axis instead. And if you, I don't know whether you watched it or not, so on the right-hand side, you saw the density matrices changing in real time as the qubit state vector changed, and you also see kind of the essentially the points to which the qubit state vector is pointing on this Bloch sphere. So now with this different phase angle on the microwave radiation that you apply to the qubit, you now rotate about the y-axis instead of about the z-axis. And as you see already in this demonstration data, which is quite a few years old, you can easily achieve quite high fidelities or quite high qualities for the qubit, single qubit gate operations. And now if you calibrate things properly, you can have 3 nines fidelity, and there's even some groups in superconducting circuits that do it a bit better than 3 nines fidelity. So this data was about 2 nines fidelity, so an error less than 1%. And in our lab, we typically, in the best experiments now, we have on many different qubits, we have errors typically below 0.5% or so. And this is really the same technique that gets used for all 2-level systems when you control their state. So in superconducting qubits, there's a number of different ways how to enact 2-qubit gates, and we use a particular version of that, and I'll only discuss that rather than discussing maybe a range of different 2-qubit gates that one could realize. And our 2-qubit gate is actually one that is initiated by tuning the qubit transition frequency in time. And so here we see the states of 2 qubits, qubit A and qubit B, and so these state vectors 2, 0, for example, refer to the state of the left qubit and the state of the right qubit. So our qubits, as I said in the beginning, because they have this cosinusoidal confinement potential, they not only have 2 states, but have higher excited states as well. And in this experiment here, in our way to realize this 2-qubit gate, we use the second excited state of one of the qubits. And here the qubit excitations are labeled 0, 1, and 2 rather than G, E, and F. So what you also see is that here this state is the left qubit in its excited state, and the right qubit in the ground state, and this state here is the right qubit in its excited state, and the left qubit in its ground state. So that you see that the 2 qubits are detuned from each other in this initial situation. And then to actually perform the gate, what it is that we do is we bring both qubits to the excited state, to this 1-1 state. So we apply 2 pi pulses to each, the left and the right qubit, or a single pi pulse to each one of the 2 qubits, and so that they're both in their first excited states. And then actually to the left qubit, we apply a magnetic field pulse that brings down the frequency of the left qubit. And actually we bring down that frequency such that this 2-0 state with the left qubit in the second excited state and the right qubit in the ground state becomes resonant with both qubits in the first excited state. And so here's a little animation of that. So we apply a magnetic field to the left qubit, and then also this 1-1 state lowers in energy because the 1-1 state also has a left qubit component. And we do that such that the 2 states are in resonance with each other. And then since these 2 qubits are actually coupled to each other through a resonator, like you've seen on my title slide, and as I've explained in the circuit QED context, these 2 qubit states can now interact with each other. And this interaction actually leads to a splitting or a hybridization between this 1-1 or 2-0 state. And this hybridization you can see as these 2 new states in frequency space. And similar, as I'd mentioned, for this time-resolved vacuum Rabi oscillations, if you start not in an eigenstate of this coupled system, like in the 1-1 state, then the system will oscillate between 1-1 and 2-0. So essentially the 1-1 state will go to 2-0. And if you double the interaction time, it will actually come back to 1-1. And the interesting bit is while you have cycled through this interaction exactly once, you're back in the initial state. But since this is a quantum mechanical system, upon this transformation, you have picked up a -1 phase factor in front of your 1-1 state. And now you could also look at what would have happened if you had started in the 0-0, 0-1, or 1-0 state. And if that would have been the case, yeah, then then none of these other states would have interacted with anything else. So they would have just stayed where they are. And what that means is that those states would have remained the same even when you detune the qubits back to their original transition frequency. And so the 3 other states, 0, 1, 1, 0, and 0, 0, acquire no phase factor, while the 1, 1 state acquires a phase factor. And this actually one uses to create a so-called controlled phase gate. And the unitary that belongs to that is the unitary that is shown here, which has 1s on the diagonal and a -1 in the last entry that describes this phase change for the 1-1 state. And together with single qubit gates, this C phase gate can actually be turned into a C0 gate, and therefore is one of the components for performing universal quantum computation. So this is a universal 2-qubit gate. And so this C phase gate is typically depicted by the qubit lines run horizontally, and when you do a C phase gate between the 2 qubits, it's indicated as these 2 bullets linked to each other by a line. And to turn that C phase gate into a C0 gate, to one of the qubits, you apply 2 single qubit rotations. And here in this notation here, R stands for rotation, single qubit rotation, Y indicates the axis about which is rotated, and pi half says the angle about which it is rotated. And if you do this 2 single qubit operations, this actually turns the C phase gate into a C0 gate. And this we'll use later in this error correction experiment or error detection experiment. So what can you do to verify that this actually happens in this experiment? So what we do in the experiment, we bring both qubits to the excited state, then we apply magnetic flux to one of the qubits to bring it into resonance with the other one, reduce the flux again, and look at the final state. And to see that this C phase gate works, one of the characterization measurements that one can run is the so-called process tomography. And in process tomography, you ask yourself, if you have some process E applied to some initial state characterized by some density matrix rho, what will be the resulting density matrix after you applied that process? And one of the ways how to determine that is to actually decompose this generic process E into an operator basis EK. And this operator basis for every individual qubit is just the identity matrix and the 3 Pauli operators X, Y, and Z. And you can essentially decompose any arbitrary process acting on n qubits into an operator basis expressed process that combines identity and Pauli operators on each one of the individual qubits. And the element that then describes that process is the so-called chi matrix here, or the process matrix. And this process matrix defines or describes the weights with which these operators act on this initial density matrix rho to produce the final density matrix rho prime. And to actually measure this process matrix chi, you feed all possible single qubit states to the input of that process and do tomography at the output of the process. And from that, you can then, with some linear algebra, reconstruct this chi matrix. For example, for the C phase gate, which we've done here, and the gate fidelity for this example was 99% or so. And in our lab, typically we can do gates with fidelities around 99%, but in larger devices, at times the fidelity is also a couple of percent lower than that. And as I said already before, you can turn the C phase gate by this 2 extra single qubit rotations into a C0 gate, which is then the archetypical gate that 2 qubit interactions are expressed in quantum information processing. Good, so that's all I wanted to say about 2 qubit gates in superconducting circuits, and in particular picking the example that we use in our own lab, and that's also widely used by other labs, but there's also many other 2 qubit gate realizations that get implemented by other academic and industrial groups in the field. So I want to say a few more words about Qubit Readout, before I then switch to the final topic of how to do error correction or error detection in superconducting circuits. So here you see a little patch of the device that we discussed already in the beginning. So there's this superconducting qubit shown in yellow. It has this microwave frequency control line in green for applying single qubit pulses. Oh, sorry, that's wrong. So the green line is the flux line that tunes the qubit transition frequency, and this pink line is the one through which we apply microwave frequency pulses. And then the readout gets done by coupling a microwave frequency resonator to this yellow qubit, and that's this reddish lambda quarter resonator that has an open end on the qubit side and is shorted on the other side. And this lambda quarter resonator acts as that resonator, the frequency shift of which we measure to determine the qubit state. And then that's not directly coupled to an input line, but coupled through this Purcell filter here, which you see looks essentially the same. It's another microwave frequency lambda quarter resonator tuned to the same frequency as the readout resonator frequency, and the two are coupled to each other. And the combination of the two is coupled to some feed line here. And actually the sort of the white strips that you see here are air bridges. So on this chip, there is we can realize some crossovers and connections between the ground planes using these air bridges. I need a cup of water. Maybe I can take a question while I drink some water. Or
okay, there are no questions in the chat, but we are encouraged to ask questions. If you have something that would like to know or something that didn't understand well.
Okay, if there's no further question, I had my glass of water. Let's hope that
actually, there is a question that was asked, so maybe we can answer. So why is the QCHS said to be an electronic photon on these slides? Photons don't have any energy levels. This is the question. I think you're muted. I can't see if you're speaking.
Okay, yeah, that that I didn't notice. Sorry. Now I'm coughing again. Sorry.
If you want, you can take another glass of water. We can have another break.
No, that's fine. So okay, so I was so these resonators, they can you can actually load them with individual photons if you want to. It has a linear energy level spectrum. The ground state has no photons, and then you can add photons one by one, for example, by loading them through the qubit, through interactions with the qubits. Or you could also put coherent states into these resonators, for example, by taking a coherent radiation source that you apply through this input port to this resonator. And then actually for all these readout experiments, we use coherent tones. And coherent tones are Poissonian distributions of photon numbers with a given phase that populate the resonator with an electric field with a minimum uncertainty, amplitude, and phase as allowed by quantum physics for the coherent states. I hope that at least did catch the right direction of the question. So I said that there is this red part is the readout resonator, the blue part is the Purcell filter. The special thing about this chip was that there's multiple of these resonators coupled to a single readout line so that we can frequency multiplex. What is also special is that there's a large coupling between the qubit and the readout resonator. And this large coupling leads to a large dispersive frequency shift. That means that the resonator shifts a lot in frequency when the qubit changes state. And that's convenient for doing high fidelity readout. Excuse me. Good. And another important aspect in this readout is you need to be able to detect the microwave radiation that gets scattered off these readout resonators effectively. And in superconducting circuits, we do that using parametric amplifiers. And these parametric amplifiers, they can detect microwave frequency radiation close to the limits that are allowed by quantum physics. So they can add very little noise to the signal and then enable a high fidelity detection of the qubit state. So here you actually see an example of what I've explained previously. So this is a transmission spectrum of the readout resonator with its Purcell filter. So if there was only a readout resonator, you would see a single Lorentzian line, but now we have essentially 2 lambda quarter resonators coupled to each other. And the coupling combination which you choose leads actually to the spectrum where you have kind of a broad envelope and a dip in the middle of it. And this comes from the interference between the radiation interacting with this Purcell filter readout resonator combination. And we measure that spectrum then once for the qubit being in the ground state and once for the qubit in the excited state. And what you clearly see is that the spectrum is shifted in frequency by a fair bit. So this axis here is scaled in gigahertz, and the frequency shift between the 2 states is roughly 16 megahertz or so. And the width of these lines actually tells you about the bandwidth of this readout resonator. And the wider these lines are, the faster you can get photons into the readout resonator and out of it again. And this combination of Purcell filter and readout resonator is used to have large photon decay rates while not affecting the qubit lifetime too much. Okay, and then so essentially you can then choose an operating point, you choose some frequency, and then you measure the transmission through the resonator depending on whether the qubit is in a ground state or an excited state. And here you see transmission amplitude. So it's not decomposed into 2 quadrature amplitudes. There was this question before that was asked whether you should measure amplitude or phase or power, for example, or any of the quadratures. And effectively in our experiment, we measure 2 quadratures. But in this plot here, there's the transmission spectrum shown in amplitude. So if you want to do a good readout, when you look at the amplitude, you would pick a frequency at which the 2 amplitudes are as different as possible. And so for this demonstration experiment, we have then done that. So here you see what is plotted on this graph here is what happens when you apply a readout pulse to this readout resonator. This readout pulse starts at the time t equals 0. And then the resonator gets populated and we measure a transmission amplitude through that resonator and how it depends on time. Once for the qubit being in the ground state, and then also for the qubit being in the excited state. And sort of a single measurement trace actually looks like this a wiggly curve with dots that are connected by straight lines. And then if you repeat that experiment a couple of thousand times, and average, you find the average light blue curve. And the standard deviation of the distribution at every point in time is indicated by the wide band that you see in the background. But you clearly see that each individual curve for the qubit in the ground state looks roughly like that. And when you compare it, for example, to an excited state, each individual excited state curve looks distinctly different from the ground state curve. Yeah, so and that comes from the resonator frequency shift that is induced by the qubit state change. And here again, like the red data set is an individual measurement. So where you prepare the qubit once in the excited state, you switch on your measurement once, you digitize the measurement data, and the solid line is one where we averaged over a few thousand traces, and the standard deviation is shown again by this orange white band in the background. And then to actually determine the qubit state, what you do is you integrate that detection signal over time, over a given time window that is indicated by tau, and where tau measures the time from the moment that you switched on your readout tone until you stop considering the data. And now you see the 2 data sets again, and you clearly see that both for individual traces and on average, you can clearly distinguish ground states from excited states. And the typical characterization measurement that you then frequently do is you pick an integration time tau, say 50 nanoseconds or 100 nanoseconds, and you integrate the readout signal over that time. And then you put that value into a histogram. And you condition the histogram on whether the qubit was prepared in the ground or in the excited state. And you look at what that histogram looks like. And on this slide, you see such a histogram. So here's the integrated measurement signal on the x-axis. You've seen every time that the qubit is in the ground state, the integrated measurement signal is negative. And the distribution of the integrated measurement values is shown by this histogram here. And you see that it's roughly Gaussian. And there's a distinct other distribution for when the qubit is in the excited state. It's also Gaussian. And the two distributions are shifted from each other. And for the excited state, you also see that even at this short integration time of 56 nanoseconds, there's some finite probability that the qubit will have decayed to the ground state before you've finished your integration time. And mind that this is a logarithmic scale here, so there's very few counts in this part of the histogram here, which identifies the states or the instances where the qubit had already decayed to the ground state while it was prepared in the excited state and then measured. And the quality of the measurement you can now actually characterize in different ways. And one of the ways is to consider the overlap error in these histograms. And the overlap error is actually one that reduces as you increase the integration time. So when you increase integration time, essentially the histograms move apart from each other and the overlap error gets reduced. But as you increase the integration time, then the qubit, when it was in the excited state, has more opportunity to decay. And therefore, the error in the state identification due to qubit decay increases. And there's also another error source, namely that there is a small probability that the measurement itself might change the qubit state as well. And so one of the things that we've looked at, we've checked both versus integration time and versus measurement field strength, how the measurement error actually varies across these parameters. And here's the data set that shows measurement integration time, shows the measurement error versus measurement integration time. And when the measurement integration time is very small, the measurement error is large. And as you integrate more, the two readout signals, they separate from each other. You saw in this plot on 2 slides ago that the ground state trace did go to low values and the excited state trace did go to high values. And they get more and more distinguishable the longer you integrate. And then there's an optimal integration time scale, beyond which then you start to get errors that stem from the qubit decaying from the excited state to the ground state. And at that integration time, you then get optimal fidelity. And for the example that you see here, you get a fidelity of about 99% in about 50 nanoseconds or so. Okay, so this kind of concludes this single qubit gate, 2 qubit gate, and readout part. And I have a couple of slides that I don't think that I have time to discuss, but I'll just leave here for a second. You can hold it up later. So these slides show you some examples of recent work in quantum information processing with superconducting circuits. So there's lots of basic works has been done in the past 15 years for demonstrating all the elements. And currently in quantum information processing, the work is focusing on implementing schemes for error correction and also implementing so-called NISQ-based approaches. So implementing algorithms that might result in sort of interesting outcomes without requiring quantum error correction to be implemented. And so those fall into different categories. Namely, you could perform digital and analog quantum simulations with these mid-scale superconducting circuits. And a particular example of that is, for example, work on quantum chemistry. So there's quite a bit of interesting experimental efforts that use mid-scale superconducting circuit devices, say with several tens of qubits, to perform quantum chemistry simulations, essentially calculate ground state and also excited state energies of small molecules, and kind of try to point at how that could be a useful approach for quantum simulation with superconducting circuits and also with other quantum information processing systems. And maybe a third application area is using small-scale superconducting circuits for quantum approximate optimization algorithms, where you find an optimal solution by running a quantum algorithm on a superconducting circuit. And here's a few examples of those. And also our own lab has worked on that a little bit. Good. So, and the last 20 minutes or so that I have, or I know it's more 15 that I have, I'll tell you a little bit about quantum error detection and error correction. So you probably all have heard about this quantum computational supremacy experiment by Google that was now done maybe close to 2 years ago, and it used 53 qubits on a 54 qubit chip. Everything was working really quite nicely on their chip. So they had 2 qubit operations with less than 1% gate error. They had even better single qubit operations on this device that were significantly less than 1% error. Their readout on this device was good, maybe not quite as good as the readout that I presented in the last slide, but they had a much more complicated device with many more qubits to read out. And what they've implemented on this device was kind of essentially a randomly chosen gate set that would create a very complicated entangled multi-particle qubit state at the end of this random gate sequence. And then they tried to simulate that random gate sequence outcome on a classical computer and showed that that's very hard to do on a reasonable timescale. So in that sense, the quantum computer outperformed the classical computer in creating a proper quantum state at the output, which had the desired statistical properties. But one of the aspects that is important to point out in this quantum supremacy experiment, the fidelity with which the final state of this 50 qubit processor corresponded to the one that you were expecting was only about 10 to the minus 3. So the final state is not very close to the ideally expected state. And this indicates that in the end, you need to be able to correct for errors that occur, both errors that are induced by the gates themselves and also decoherence errors in these circuits. And one of the ways to do that is to make the quantum computer fault tolerant through quantum error correction. And quantum error correction, I'll essentially spend a few minutes to explain the concept. So rather than encoding your quantum information directly in physical qubits, where every single qubit actually stores 1 quantum bit of information, in error correction, you try to, at least in the surface code version of error correction, you distribute the quantum information across a larger number of so-called data qubits. And then you try to measure properties of this data qubits using so-called ancilla qubits without destroying the quantum state of the data qubits. And one of the approaches called the surface code is shown here. So there's this square array of data qubits shown in red. So it's a 5 by 5, so 25 qubit array of data qubits. And you try to store your quantum information in sort of a complicated entangled state of these data qubits. And then these data qubits are interspersed by so-called ancilla qubits that couple to 4 nearest neighbors. And these ancilla qubits can be used to measure certain symmetry properties of the data qubit states. And I'll explain that in more detail in a second. So this device or this layout that you see has 49 qubits. And for the experts among you, that would be it would be big enough to realize a distance 5 surface code. So let me say a bit more about these data qubits and the ancilla qubits and what they're used for. So the ancilla qubits come in these 2 types, so-called X and Z ancillas. And these X and Z ancillars, they measure different symmetry properties of the quantum states stored in the 4 neighboring data qubits. And using these ancilla qubits, you perform so-called stabilizer measurements. So you measure these combinations of 4 Z operators in a weight 4 stabilizer or 2 Z operators in a weight 2 stabilizer along the Z axis. Or you can do the same thing in the X axis. So you measure the expectation value essentially of the combination of the X operators, X1, X2, X3, X4, where the the indices 1, 2, 3 relate to the coupling of this ancillar qubit here to the 4 nearest neighbors data qubits. And at the edges, there's ancillar qubits that measure the parity or this stabilizer when they couple to just 2 neighboring qubits. And how do these stabilizer measurements work? In these stabilizer measurements, you essentially perform C0 gates between each data qubit and one of these ancillar qubits. And since in our circuits, we don't realize C0 gates directly, but these C-phase gates, which I've explained to you before, here the 2 qubit gates are indicated as the C-phase gates with indicated by these lines that connect the data qubit with the ancillar qubit. And to effectively turn these 4 C-phase gates into 4 C0 gates, we use single qubit gates in addition. And you see that the single qubit gates that sit in between the 2 qubit gates, they just cancel each other out because they all act on the same ancillar qubit. And what this gate sequence here does, I'll explain at a more simple example on the next slide. So this circuit here performs the so-called Z stabilizer measurement. And if you flip the basis of the data qubits by applying pi-half pulses to them, and then apply the same gate sequence, you can also measure the data qubits in the X basis and thereby perform an X basis stabilizer measurement. And for that to work well, you see that you need to apply quite a number of 2 qubit gates and also single qubit gates, which all have to happen in high fidelity because this error correction code relies on being able to measure the symmetry or the parity of this 4 qubit stabilizers with high fidelity so that you can actually tell whether an error occurred or not. Okay, and this whether an error occurred or not, you can actually find out by after this gate sequence performing a measurement on the ancillar qubit. So in this error correction scheme, you need to be able to run these gates very effectively with high fidelity and also be able to measure the ancillar qubits without disturbing any of the data qubits. So let's maybe explain how this parity or stabilizer measurement works in a weight 2 stabilizer example that is simple. So here you would measure the Z1, Z2 stabilizer for 2 data qubits. And you essentially apply a C0 gate between each one of the data qubits and the ancilla. And now if the C0 gate, it does nothing when the qubit is in state 0. Yeah, so essentially for the 0-0 data qubit combination, the ancillar qubit just stays in its ground state where it's been initialized initially. When both qubits are in the excited state, the 2 C0 gates will subsequently flip the ancillar qubit first from the ground to the first excited state and then back from the first excited state to the ground state. So when you have an even number of 1s or an even number of 0s in your data qubits, yeah, the ancillar qubit will remain in the ground state. And that indicates an even parity data qubit state. So an even parity says that both qubits are in the same state. So either both 0 or both 1. While when the data qubits are in an odd parity state, say one of the qubits is in the ground state and the other one is in the excited state, then one of the C0 gates will flip the ancillar qubit from the ground state to the excited state. And now your ancillar qubit tells you that your data qubits are in odd parity state. And so now the whole idea of the surface code is to encode quantum information in states with a given parity. So you would decide, for example, to encode quantum information only in states with even parity, say where there's the same numbers of 0s and 1s. And if that's the case, then the ancillar qubits always stay in the ground state. And if then an error occurs, yeah, one of the qubits will flip from either the excited state to the ground state or from the ground to the excited state, your ancillar qubit will tell you that the parity changed from even to odd. And this parity change you use to actually identify whether an error occurred or not. And the interesting thing is in the surface code, you can do that without learning the state of the logical qubit that you have encoded in your data qubits. And that's what I explain a bit more on the next slide. So here's the, on the surface code here, we don't implement a distance 5 surface code on these 49 qubits, but the first thing that we did in our lab is we implemented the distance 2 surface code on just 7 qubits that you see here. And so there's 4 data qubits and 3 ancillar qubits. And so as you see here, there's 1 blue ancillar qubit that measures the X parity and 2 green ancillar qubits that measure the weight 2Z parities. And the interesting bit is that this set of stabilizers, they commute with each other. So these 3 operators commute with each other, and therefore they have joint eigenstates. And for example, in these joint eigenstates, you can then encode the logical qubit. And so you could encode the ground state in this combinations of zeros and ones of the 4 data qubits, and the excited state in this combinations of zeros and ones. And you see that both of these states have both even parity. And now, for example, if one of the qubits would flip state, then that would be indicated by an ancillar-based parity measurement as a state change in the ancillar qubit. And that allows you to identify whether an error occurred. And logical superposition states are then superpositions of these basis states, and they obey the same properties. And so you're allowed on these states to measure their parity without actually learning which state your logical qubit is in. And that's the whole key idea of quantum error correction, that you can perform measurements to identify whether errors have occurred without learning the quantum state that you've stored in this logical qubit. And this is really the simplest example that you can realize there. And then you can perform logical operations on these qubits by actually applying logical operators on them. So to flip the logical qubit state, you can perform this x1, x3 operator on the 0 state, and that will actually flip the second and the will flip the first and the third qubit from the ground to the excited state, and thus turn a qubit excited state into a qubit ground state. And these logical operators then anti-commute with the stabilizers. And that's what you want, anti-commute with each other. All right, and so I have virtually no time left, and so I can maybe only give you the idea of the experiment. So here's the device that I've explained to you in the beginning with its 7 qubits, and you now should be knowing what all these different elements on this circuit are used for. So here you see how you would identify the 4 data qubits, D1 to D4, and 3 ancillar qubits. Here's sort of some parameters about the performance of these qubits, like their lifetimes and their transition frequencies and how well we can read them out. And essentially, we can perform very good single qubit rotations on every one of those qubits with much less than 1% error. And on this device, the 2 qubit operations were actually worse than what I've explained to you before. They're somewhere on the, say, 2 to 4% level. But overall, this device was good enough to actually implement this distance 2 error detection algorithm. And this was actually the first time that the surface code distance 2 error detection was implemented in any superconducting circuit device. And obviously, this is based on quite a bit of prior work that was done in other labs and also in industry on error detection and error correction. So we used elements that have been tried out before. But this, for quite some time, for about a year, was the sort of the best error correction and detection experiment in superconducting circuits. And by now, Leo Di Carlo's lab and both IBM and Google have equivalent experiments that realize this distance 2 error detection circuit. Okay, and So I think now we're essentially out of time, and I've been able to explain to you the idea of the surface code distance 2 error detection. And now I should probably ask Uwe how we proceed here. I could just wrap it up and take a few more questions and then let people go for their lunch.
That's a good idea. We have actually 3 questions in the chat here, and there were a few more on the YouTube stream. So we have ample questions to fill a few minutes.
Good, we could do that. I should probably also say is that I've presented this the work on the error detection at a number of other occasions, and maybe we can put a link for that. So those of you who are interested in the details could look at that, and I could take a few more questions.
If you have the remaining slides available, we can also distribute them.
Yeah, I could do that.
So that if you just send them to us, we'll upload them. Cool. Francesco?
Yeah, okay. So if you want to, you can also read. But okay, the first question is, in the readout, is there one error type preferred over the other? Maybe because of it applies to both the sets equally?
Yes, so I think the decay error is more prominent because the qubit will decay from the excited state to the ground state, and so that error source occurs more often. And the ground state, unless there's thermal excitation or measurement-induced mixing, the ground state error should occur with a smaller probability. Yeah, so in many instances, the residual error is limited by excited state decay at a given integration time.
Okay, so another question: how to make sure that performing CNOT gates between 2 qubits doesn't couple other qubits that are not meant to be used?
Mm-hmm. That's a very important question. We've looked at that a fair bit. So one of the aspects that you need to make sure is that there's no unwanted interactions with the neighboring qubits, and so you have to arrange them in frequency space such that no interactions occur. So in particular, in the surface code lattice that you've seen, a single ancilla qubit couples to 4 neighbors, and you have to stagger the data qubits and the ancilla qubits in frequency space in a way that you can target a certain coupling and have preferably no or only very small residual couplings to other neighboring qubits. But this residual qubit coupling is actually a challenge, and we've addressed it also in a paper where we've analyzed that a bit, and it's sometimes discussed in the terms of the role of spectator qubits in these larger devices.
Okay, then they want to know if bosonic codes can be implemented in your experimental setups.
Okay, so one thing that I really didn't have time to explain in more detail, or I haven't even mentioned at all, is that this surface code error detection is a qubit-based, or surface code error correction is a qubit-based error correction code. You can also consider error correction codes based on bosonic systems, yeah? and those can be realized, for example, in the oscillator modes of ions, or in resonator oscillator modes in these superconducting circuit devices. And this is also very successfully done, and maybe in terms of performance of the logical qubit, this is even a bit ahead of the surface code implementations. And one of the labs that really does pioneering work there is the other groups of Rob Schilkopf and Michel Devereux at Yale, for example. So you could look at their work there. And I think I also had a few citations on one of my slides on that bosonic code work.
Okay, then a question on error correction. They want to know if there are alternatives to the surface code that require less ancilla qubit for each, let's say, logical qubit.
I think there's a wide range of different codes that could be used. The surface code stands out as one that has the highest error threshold. Yeah? So in the end, what you need to achieve is that, say, the single and 2 qubit gate fidelities and also the readout fidelities and all our other errors need to be lower than a certain threshold, so that the logical qubit actually performs better than the physical qubits. And that's very demanding. And the surface code is the one which is most tolerant to errors occurring. and other codes are typically less tolerant to errors occurring, and so have even more stringent requirements on the gate and readout errors. But there's lots of literature on different codes and exploring different codes, and maybe looking at codes that are more targeted towards certain error sources is also an interesting subject of research.
Okay, then since we are quite advanced in time, I would ask a last question that comes from YouTube. So the question is, does the implementation of the C phase use an AC or DC pulse? And does this implementation also cause leakage effects?
Yes, so the C phase gate that I've discussed is based on a DC pulse. And indeed, there is the possibility of leakage occurring in these gates, in particular because you use the second excited state of one of the qubits. Yeah? And for example, if you don't manage to remove all the excitation from this qubit that cycles through its second excited state, that can lead to leakage, and that needs to be suppressed. Yeah? And it's one of the error sources in this 2-qubit gate, which is particularly detrimental, for example, in error correction settings, where like leakage errors are particularly difficult to recover from. So that's a good question.
So I think we are done. Thank you very much for the talk that I would say resonates very well with the spirit of our school. And so now we can have lunch. There is 1 hour approximately of lunch break. We'll be back at 2. There is the talk of Dario Gil from IBM. Remind that the link is not the same of this webinar. It's another link webinar, and you can find it on the leaflet of the school. So we'll be back at 2 on the other link, and then there is the tutorial.
All right, thank you very much. Thanks for having me. Sorry for the technical problems in the beginning, and also the technical problems with my voice and being out of time a little bit, but I hope you still got something valuable out of this contribution.
Thank you very much.
Absolutely, thank you very much.
It was a great talk.
Thanks. So do I send you the slide set, or?
Yeah, if you just send them to me by email, and then after the school, when we also send the link for the recordings, we'll just include the slides. I think Vincenzo also already sent us his slides, and we'll just keep collecting while we go, and then next week or so we distribute them.
All right. Yeah, thanks a lot. Sorry for the technical difficulties.
Yeah, absolutely no problem.
No problem. Absolutely.
We have large breaks in between.
All right. Thanks. Cool. Bye-bye.
Bye-bye.